Hi students, today I am going to discuss about the topic B trees in the subject data structures. The subject code for this subject is CS8391. It comes under unit 3, that is nonlinear data structures trees. The main objectives of this presentation are learning about the basic concepts behind B trees and solving some problems using the B trees. That is how to insert the value, how to delete the value from the B trees. So they all are we are going to discuss in this video. So the B trees, the main motivation of B trees is it is a dynamic set that is optimized for disk access. So B tree is mainly optimized for disk access. So B tree is M-way search tree. Okay, that is M, you can give any value. So M can take 2, 3, etc. If M is 2, it's called as two-way search tree. If M is 4, it's called as four-way search tree, and so on. So generally, B tree is an M-way search tree. It has the following properties. B tree should be perfectly balanced. That is, every leaf node is at the same depth. They all should be at the same level. Every internal node other than the root node is at least half full. Okay, that is, if the degree of the B tree is M, then every internal node other than the root node, it should be at least half full, that is M by 2 minus 1 and M minus 1. Okay, the number of keys should be in the range M by 2 minus 1 and M minus 1, where M is the order of the tree. Every internal node with the keys K, they can have K plus 1 non-null children. So consider the second point. So now we are rewriting the condition as like this. That is, normally we choose M as the even number and use T equal to M by 2. So substitute this in second property. So T is M by 2. So M by 2 minus 1 is nothing but T minus 1. Less than or equal to number of keys less than or equal to M minus 1. So T equal to M by 2. So what is M? 2T. Okay, 2T minus 1. So number of keys should lie between T minus 1 and 2T minus 1, where T is M by 2. Okay, M is the order of the B tree. So example, 4-way binary tree. So what is B tree? It should be perfectly balanced. Every leaf node should be at the same depth. Every node except the root node is at least half full. That is, the number of keys should lies between T minus 1 and 2T minus 1. Every internal node with K keys has K plus 1 non-null children. Now we are going to see the procedure for insertion. Okay. So we have 3 steps for insertion. First we have to find the leaf node to which X should be added. Then you can add X to this node in the appropriate place among the values already there. That is, we should maintain the ascending order. If the number of values in the node after adding this particular key is fewer than 2T minus 1, then no problem. Insertion is completed. But if the number of values or the number of keys is equal to 2t, it indicates that it is overloaded. Okay, if it is overloaded, you have to fix the overloaded node. So that's about the procedure for insertion. So we have 4 steps. First we have to find out the leaf node. Okay, then you have to add x into that leaf node in the appropriate place. That is, you have to strictly maintain the increasing order. Then count the number of values. If the number of values is less than 2t minus 1, then okay, no problem. If it is equal to 2t, it indicates that the node is overflowed. So you have to fix the overflowed node. We will see with one example how to fix an overflowed node. Okay. So we have to split the node into 3 parts. That is, if the node contains 2t values, then you have to split that node into 3 parts. One is left, second one middle, third one right. So left is the first t values become a left child node. The middle value at position t, it goes up to the parent. The last t minus values become a right child node. Okay. Then the same procedure is applied with the parent also until no overflow occurs in the parent. If the overflow occurs at the root, then root is also splitted into 2 nodes and you have to create the new root node. Okay. So for example, in x, I am having the values 56 and 98, and in y, I am having 60, 65, 68, 83, 86, 90. So 68 is the new inserted node. So it is overflowed. So what I need to do, I have to find the first t values that becomes a left child node. That is 60 and 65 becomes the left child node. The middle value at position t, it goes up to the parent. So 68 is the middle value. So it is moved up to the parent. The last t minus 1 values, that is 86, 83, 86, 90, that becomes the right child node. Okay. So then again you have to check the number of values in the parent node. If the number of values in the parent node exceeds a particular limit, if it is overflowed, the same procedure is repeated. Okay. So we will go with another one example. So see, m is equal to 6. Okay. The order, the B tree of order 6. So what is t then? T is m by 2. Okay, t is m by 2. So now we are going to see an insertion example. So we are going to insert the value 3. So 3 is less than 20. 3 is less than 20. So use this link, and this one is the corresponding leaf node where I have to insert the node 3. And 3 should be inserted in the proper place. That is, you should not insert like this 0, 5, 10, 15, 3. It is wrong. Okay. It should be inserted 0, 3. Then the new node. 3 is the new node. 0, 3. Then 5, 10, 15. It should be inserted in its right place. Okay. Then check. Then count the number of values in the leaf node. So it is 5. So not at all a problem. So we will move with another one example. See, I am going to insert the node 61. Okay. So 61 lies between 60 and 80. Okay. So 61 is greater than 60. So we have to move into the right child. So after insertion, the node looks like this: 61, 62, 66, 70, 74, 78. it is overflowed. Okay, so the number of nodes, so see the condition. What is the condition for insertion? If it is less than 2t minus 1, then no problem. If it is equal to 2t, then it is overflowed. Okay, so here it is equal to 2t. Number of nodes is equal to 2t. That is 2 into 3, 6. So it is overflowed. So how can I fix this? I have to split this node. Okay, so that is the element at position t is moved up to the parent, and the left side values becomes the left child and the right side values becomes the right child. Okay, that is the middle element is moved up to the parent, and we are splitting the particular overflowed node into two child. So that is 61, 62, 66 becomes the left node, 74 and 78 becomes the right node, and the node 70 is moved up to the parent. Okay, so that's all the insertion. So we will see with another one example. Insert 38. So 38 lies between 20 and 40. 38 is less than 40. So this is the right node where I have to insert 38. So after insertion, the node looks like this: 25, 35, 38. Then count the number of values in this leaf node. So it is 3. So it is not equal to 2t. So no problem. It is not overflowed. We conclude this. Okay. So similarly, we go for deletion operation. So in deletion operation, what is the problem means? We have to check for the underflow. For insertion, you have to check the overflow, and for deletion, you have to check for underflow. So what is underflow? The number of keys remain in a node is less than t minus 1. Okay. If it is like this, then that node is underflowed node. So don't forget, the root node should have at least one value in it. Okay. And all the other nodes should have at least t minus 1 values. Okay, at least t minus 1 values must be there. So if it becomes less than t minus 1, it indicates that the particular node is underflowed. So how to fix this? So we will see with one example for underflowed node. See, I am deleting the value 87. After deletion, the node looks like this. It contains only one element. But what is our condition? It must contain at least t minus 1 values. Okay. So here the t is 3. So t minus 1 means 2 elements. At least except the root, all the other nodes must contain 2 values. But here after deletion, the node contains only one node. So this is an example for underflow. So how we are fixing this problem, or what is the solution for this problem means, you have to make sure a node that is visited has at least t instead of t minus 1 keys. That is, if the node contains t keys, then you can choose that node for deletion. Okay. So for example, in B tree deletion, we are going to see about 2 cases. One is deleting the leaf node and the other one is deleting the internal node. Okay. So assume in the first case, k is in x. That is, we are going to delete the element 66. It is in x. Okay. So if k lies in the leaf node, then you can delete the node. You don't need to worry about anything. After deletion, the node looks like this. Then you check for the number of keys. Okay. So if it is not underflowed, then no problem. In the second case, if the k is the internal node, okay, if k in the internal node x, that is k is in the internal node x, that is k here is 50. So this is the element what we are going to delete in this example. So it lies in the node X, and Y and Z are preceding and succeeding nodes, and Y is the preceding node. Similarly, we have Z, so it is the succeeding node. Okay. If Y has at least T keys, so what is the condition? We have to look for the node which must contain at least T keys. Okay. So here Y is having T keys, so no problem. So you have to replace K by K's predecessor of K in Y. Okay, so you have to replace K. You have to replace K. Okay. K in X is replaced by the predecessor of K in Y, that is 45. So 50 is replaced by 45 after deletion. So that's all. Okay. So similarly, you can do with the same type of deletion with successor node also. In the second case, if both A and B are not satisfied, okay, Y and Z have T minus 1 keys. What is the condition? We have to choose the key which contains in the second case of deletion, that is if suppose both A and B are not satisfied. So what is A and B? If Y has at least T keys, similarly if Z has at least T keys, that is both the preceding node and the succeeding node must contain T keys. But if it is having T minus 1 keys, then how can we perform the deletion operation? Okay. So in this case, you have to merge the two children. You have to merge the two children Y and Z. You have to merge the two children Y and Z. See the figure. I am going to delete the element 50 from the node X. I have to look for its preceding node and succeeding node, and Y is the preceding node and Z is the succeeding node. But the values in both Y and Z are T minus 1 keys. They are not T keys. They have only T minus 1 keys. In this example, we have taken M is 6 and T is M by 2, that is 3. Okay. So they are having only 2 children. So how can you perform the deletion operation? You have to merge the two children, that is 35, 40, 55, 65, and you have to recursively delete K from the merged cell. Okay, 50 is moved down and it should be deleted recursively. So that's about the deletion process in B tree. So these are some gate questions. Okay. So this is sample Anna University questions. So with this I am concluding today's topic B tree. Thank you.